think we are live, right? Yep, we are live. As far as I can see, we are live. So I'm just going to that. Um, so that is where the membership page exists. So if you want to get the membership page, it is only $3. So first of all, hi everyone, welcome to the live lecture for. Actually, let me change the title. So I am going to change the title. My channel, Kick, and Twitch. I need to also change. Obviously, it's going to take time. Definitely, it's going to take time, right? Definitely, it's going to take time. Um, I know why. Start and start. Quantum mechanics, chapter 2, time independent Schrodinger equation. Quantum mechanics, chapter 2, time independent Schrodinger equation. Right. Hello, everyone. So, and welcome to our first live stream where I will be live streaming the lecture. And I hope you can see my screen. If not, now I hope you can see my screen. We will be starting off with chapter 2, and for anyone wondering where do we get the chapter 1 from, that exists on my YouTube channel and on my membership page that is shown on the bottom right there. It's right there. You can see that zakirsadahmed.com. You can go there and check. But we will be beginning with chapter 2. So we're going to start off with chapter 2.1. This is the time independent Schrodinger equation. So to begin with this chapter, we're going to first go with the time dependent Schrodinger equation. So step 1, that is our time dependent Schrodinger equation. So what do we know about the time dependent Schrodinger equation? It is pretty simple. So we have iota h bar curl psi of x and t by curl t is equal to minus h bar square upon 2m curl square psi by curl x square plus v of x psi of x and t. And the only reason we write psi of x and t is because the wave function, because in quantum mechanics everything is represented in the form of psi, right? What we know, we did that in chapter 1. So in quantum mechanics everything is represented in psi of x and t, or psi, right? Psi. Like if you say in classical mechanics, you represent in x, or you represent in t, or you represent in whatever, right? So in common sense scenario, in common scenarios, you represent in x, right? Instead of psi. So you represent in respect to x instead of psi. But in quantum mechanics, you represent in psi because everything is probabilistic. What do we know? What do we know? So what we presume about psi of x and t. So what is psi of x and t? Now, obviously, psi of x and t, first of all, is a time dependent wave function. So it is simply psi of x, phi of t. This space derivative, and this is time derivative. So we have space derivative and we have time derivative. And when we look at the equation, let's write the equation again. So write the equation again. So we're gonna write curl psi by curl t is equal to um, minus h bar square upon 2m. Actually, I think I h bar curl psi by curl t minus h bar square upon 2m curl square sub psi by curl x square plus v of x psi of x and t. Now, obviously, if I have psi of x and t, now if I were to substitute into the equation, now when I look back here, curl psi by curl t, if I write psi of x and t, can you guys see my screen? Okay, let me do one thing. Close that. Close that. I'm just trying to make sure that you guys are able to see my screen because I'm not able to always see the screen because what I have to do is actually I have to keep the app that I'm using is Lonely Screen. If I try to minimize that, you won't be able to see the screen. So I'm trying to make sure that somehow I'm going to uh like every time that will be visible, this will also be visible, so I can at least know that okay, you guys can see or you guys can't see. All right. So as you can see here, can you guys see here? I think now it's a bit better, right? So if I have iota h bar curl psi by curl t is equal to minus h bar square upon 2m curl square psi by curl x squared. So this is curl square psi of x and t by curl x squared plus v of x psi of x and t, right? And when I look at the left hand side, when I look at the equation first, what is the wave function equation? Psi of x and t is equal to psi of x, phi of t. And if I were to, we did partial differential equations, right? So if you did not do partial differential equations, make sure that you enrolled in ODEs. I am going to do live stream on ODEs too. That's completely fine. I'm going to do live streams on ODEs. I'm going to do live streams on PDEs. Completely fine. So psi of x, phi of t, and if I were to partially derivate curl psi in respect to time, then obviously this will be constant. I'm going to have psi of x curl phi of t by curl t. Typically, you don't write curl phi of t by curl t, you write curl phi by curl t, right? So what we will have is instead of this guy here, we are going to have iota h bar psi of x curl phi by curl t. And on the right hand side, we have curl square psi by curl x square. Now, this is a time derivative, right? So this is the differential equation in respect to time. This will be the differential equation in respect to space derivative. Now, if I were to look back, psi of x and t is what? Psi of x, phi of t. You guys can't see. Keep it like that. So psi of x and t is psi of x, phi of t. And obviously, if I were to differentiate this one time, I'm going to have curl psi by curl x is equal to curl psi by curl x, phi of t, right? Now, if I derive this, the same thing again, meaning second derivative, I have curl square psi by curl x square is equal to curl square psi by curl x square, phi of t. So phi doesn't change. So what I'm going to have here is therefore minus h bar square upon 2m curl square psi by curl x square, phi of t. Now if I were to bring back the Schrodinger equation again. So let's rewrite the Schrodinger equation. Our time dependent Schrodinger equation, we are going to have what? Let's write the equation again. Then let's first write the equation again, right? So iota h bar curl psi by curl t is equal to minus h bar square upon 2m curl square psi by curl x square plus v of x psi of x and t. And this curl psi by curl t was what? Iota h bar psi of x curl phi by curl t. You are free to write d phi by dt, but because you partially derivated it, it's best to write curl phi by curl t. Just take, because if you write d phi by dt, obviously you can write d phi by dt. Nobody's stopping you. Obviously you can. But at the same time, you partially derivated, so make sure that you represent the equation in a partial derivative format. So iota h bar psi of x curl phi by curl t is equal to minus h bar square upon 2m curl square psi by curl x square phi of t plus v of x. Psi of x and t is simply psi of x phi of t. Right? Cool. So this is the combination equation in respect to the derivatives that we did and the space and time and whatever. Now, one thing to focus here is that here we have space and time. Here we have also space and time. Now, what would I do to make sure that on one hand, I'm going to have one variable, let's say time only, and on the other hand, I'm going to have another variable, let's say space only. What I will do is the entire equation, which is iota h bar psi of x curl phi by curl t is equal to minus h bar square upon 2m curl square psi by curl x square phi of t plus v of x psi of x phi of t. What I'm going to do is divide the entire thing by psi of x phi of t. And so here I'm going to have iota h bar 1 by phi d phi, not d phi, curl phi by curl t. Now I can also write d phi here because now what I have is in respect to space. And the 1 by phi came because it ends up, what this actually ends up as is iota h bar psi of x curl phi by curl t divided by psi of x phi of t, this is t, is equal to minus h bar square upon 2m curl square psi by curl x square phi of t plus v of x psi of x phi of t divided by psi of x phi of t. And so obviously this will cut out. So we have iota h bar. It's best to write 1 by phi of t. So initially what you have is iota h bar curl phi by curl t divided by phi of t is equal to minus h bar square upon 2m curl square psi by curl x square phi of t plus v of x. Psi of x phi of t gets cut out. So there. And you also have 1 by psi. So divided by psi of x, right? Or you can also write iota h bar 1 by phi of t curl phi by curl t is equal to minus h bar square upon 2n 1 by psi of x curl square psi by curl x square phi of t plus v of x. Now the only way to actually solve these, so now what we have is a time derivative and we have a space derivative. We have a time derivative and we have a space derivative. The only way to be able to solve this equation is if both are stated as some constant. In this case, the constant will be, I'm going to say iota h bar 1 by phi d phi by dt. Now you don't have to write curl phi by curl d. You can, but again, it's pretty useless to write, curl phi by curl t, because it's only time derivative, right? So you can really write d phi by dt. So 1 by phi d phi by dt is equal to e. And then what I'm going to do is d phi by dt is equal to, you have e, now you also have iota h bar. When you move the in a complex value or in an imaginary value, when you try to move from left to right, you change from multiplication to division. So you have iota h bar here. Instead of iota h bar, which is a positive, you're going to have minus iota by h bar in the negative format, because one, your sign will change. Two, your operation will change. Meaning, instead of multiplication, you're going to have a division. Instead of addition, you're going to have a subtraction. So obviously, d phi by dt will be minus iota divided by h bar. E phi. This phi will also go there. And so now, phi of t will be integration of minus iota by h bar e of phi. We can do ln here, right? So this will be d phi. So you can do d phi. So 1 by phi d phi is equal to minus iota by h bar e dt. So obviously ln phi is equal to that. So minus iota by h bar e dt. And the, oh, okay. So there you go. Minus iota by h bar e dt. And so phi will be e to the power minus iota e t by h bar, because this will turn out minus iota by h bar e integration of dt, which is just simply t, right? So now what we have is our time derivated equation. Time derivated equation. So now we have, you can hear me, right? Yeah. So what we will have is psi of x and t is equal to psi of x e to the power minus iota et by h bar. And so now if I were to do the probability density, so psi of x and t whole squared, so obviously I'm going to have psi of x e to the power minus iota et by h bar. So psi of x e to the power minus iota et by h bar, psi of x e to the power iota et by h bar. And so that will cancel out. I'm going to have psi of x whole square. So what this tells us is that finding the time equation has no value. So we have the time equation, that is fine. But at the end of the day, time becomes independent, because what plays a good role or what plays the big role is not the time part, but it is the space part. So your main theory or the main objective is to make sure that you get the equation for space, because finding the equation for time, they turn out e to the power 0. This tells us that psi of x and t is the same as psi of x squared, which also tells us that it is independent of time. So like the time has no role, like in the motion, like when the quantum particle moves, when the quantum particle creates a change, there is like the time does not play a role. The time does not play a role because the time doesn't, like it doesn't exist, because initially when you are given the equation you will have time. When you do the probability density to find the probability, you will see the time vanishes. So when you are given an amplitude equation, you're going to see that you will find the amplitude, but inside the amplitude you're not going to see time, because time does not exist. time does not play any role when it comes to finding the probability of a particle. What plays the role is the space, not the time. Time has no value, right? And so from here on out, I'm just going to stop here. From here on out, what we're going to do is we are going to observe the expectation value. We're going to observe the Hamiltonian. We're going to observe the variance. We're going to observe the standard deviation. And then from there on, we'll finally find the equation for space. Because finding the equation for time, you found good, but it has no value. Finding the equation for time has no value because even if you, it's like saying you're pushing a wall. That's a very good example because the next section literally speaks about a wall. And it's like pushing a wall because you can't push a wall, it'll stay there, right? So you can go through all the time it takes to find the equation for time, but again, time has plays no role here. What plays the big role is the space, not the time. So we need to make sure that we find the equation for space, which we will be doing in the next lecture. Cool.